Welcome back, ladies and gentlemen, to another physics tutorial. Today, we are going to be talking about one-dimensional motion in a different sense, rather a different axis. We're going to be talking about up and down one-dimensional motion. We're going to be talking about the topic of free fall. But first today, we have to talk about gravity. And I'm sure you all have a sense of what gravity is. It's something that pulls us down to Earth. It's something that keeps us from floating away. But as physicists, we want to define gravity in a more rigorous manner. So first of all, what is gravity? Well, gravity is something that we call a force. Gravity is one of the four fundamental forces, along with the strong and weak nuclear forces and the electromagnetic force. So gravity is a force, and it's something that pulls objects with mass together. If something has mass, it is attracted to any other object that has mass by the force of gravity. And so the reason that gravity pulls us down to the Earth is because we have mass and the Earth has mass. And the mass of the Earth and our mass are attracted together through the force that is known as gravity. And so gravity doesn't just pull us downwards. It actually pulls us towards the center of the Earth. So if you are standing here, gravity is going to pull you down this way. If you are standing here, gravity is going to pull you down this way. If you're standing here, gravity is going to pull you down this way, towards the center of the Earth. Down is kind of vague, but it works on a very local level when we're just talking about our day-to-day lives, because gravity does pull us down. Because for us, down is always the center of the Earth. And so we can say that gravity is a force that pulls us to the center of the Earth. Okay? And how strong is that force of gravity? Well, the force of gravity kind of differs. If you are out in the upper levels of the atmosphere, gravity is actually going to be a little bit weaker than if you are at the Earth's surface. And the reason for that is because the force of gravity depends on two things. One, the mass of the objects that the force of gravity is interacting between. So the greater the mass, the higher the gravity. And second of all, the distance between the two objects. So because we are standing on Earth's surface, we are a little closer to the center of the Earth than someone who would be up in the upper levels of the atmosphere. And because of that, because we are closer, the force of gravity of Earth pulling on us is actually a little bit stronger than for someone 1,000 meters up in the air. And we've actually measured how strong gravity is at Earth's surface, and we know that the acceleration of an object due to gravity around Earth's surface, give or take a couple hundred meters, is 9.81 meters per second squared. That is the acceleration due to gravity. And it doesn't matter what mass you have, actually. The force of gravity will differ based on how much mass you have, but the acceleration due to gravity actually only depends on your distance from the Earth's surface. So your distance from the Earth's center, rather. So if you are an object at Earth's surface, you will accelerate downward at 9.81 meters per second squared due to gravity if no other forces are acting on you. And it doesn't matter whether you're a bowling ball or whether you are a feather, okay? Now notice that I said if no other forces are acting on you. That's because when we have other forces in place, such as air resistance, things get a little complicated. So the reason a bowling ball falls a little bit faster than a feather is because it has less air resistance, not because gravity is weaker on the bowling ball. And there are actually many experiments that people have done where people have taken a bowling ball and a feather and they have dropped them simultaneously in a vacuum. A vacuum is a region of space where there is no air and nothing filling that space. It's just pure emptiness. And we can actually create a vacuum, or at least very, very close to a true vacuum, in a laboratory. And we've done that. And we have tested dropping a bowling ball and a feather at the same time. And I'll include a link in the description of this YouTube video that you can check out so that you can see an actual experiment of this being done. But it's actually really cool. When we drop the bowling ball and the feather together in a vacuum, they land at exactly the same time, even though they have drastically different masses. And so we in physics have this magical variable that we call g, little g, and we say that little g is equal to the acceleration due to gravity at Earth's surface. And so little g is equal to 9.81, or in this class we will just use 9.8 meters per second squared downwards, okay? Remember, little g is an acceleration, meaning it is a vector, so it has to have a direction. And our direction is downwards towards the center of the Earth. So, again, little g is the acceleration due to gravity. Little g is not gravity, it is the acceleration due to gravity at the surface of the Earth, which is 9.8 meters per second squared downward, all right? We'll be using 9.8 in this class. For all intents and purposes, I don't care if you use 10, all right? If you want to round g to 10 and use 10 for g, I'm perfectly okay with that, all right? Just know that typically you will see little g as 9.8 meters per second squared, or even 9.81 if we're getting picky, okay? And so the conditions for an object to be accelerating at 9.8 meters per second squared downwards due to gravity, there are two conditions, two main conditions. Well, three really, but we'll talk about the third in a second. The main two are, it must be in a vacuum, means there must be no air resistance, and it must be at the surface of the Earth, all right, or near the surface of the Earth. We can go a few hundred meters up, we can go a few hundred meters down. In this class, really, a few thousand is fine, but if we want to be precise, we want to stay as close to the surface of the Earth as possible, because g will change if we go up or down too far, okay? Or g won't change, but our acceleration due to gravity will change. G is our acceleration due to gravity at the surface of the Earth. So, if an object is in a vacuum, okay, has no air resistance being applied to it, and it is falling near the surface of the Earth, we say that that object is in free fall. We define the term free fall as the motion of a body when the only force acting on it is the force of gravity, okay? If an object is in free fall, then the acceleration of that object is 9.8 meters per second squared downward, all right? Always, as long as we are in free fall near Earth's surface. So the two conditions, I said there were three. That's because the only force acting on it is the force of gravity. I counted that as a separate condition, but we can sum those two conditions into just free fall and at Earth's surface, okay? So the two conditions for an object to be accelerating at 9.8 meters per second squared downward are that the object is in free fall, aka the only force acting on it is gravity, and it's near the Earth's surface. So if this duck is in free fall, that means the only force acting on it is gravity, okay? We can't have air resistance. No air resistance is allowed, so we can't have some drag force slowing it down. We can't have some other applied force interfering with it, pushing it sideways or anything, okay? We can only have gravity if an object is in free fall. And so why do we care about this as physicists? Why is free fall useful? Why am I talking about this? Well, we can use this information of free fall to solve problems. And let's take a look at a couple problems in one-dimensional space. And this time, instead of talking about movement in the left and right direction or the horizontal direction, we're going to be talking about movement up and down in the vertical axes or the y-axis, okay? And so we have a problem here. It says that Bugs Bunny drops an anvil from the top of the gateway arch, 192 meters above the ground. And it asks us, what is the velocity of the anvil just before it hits the ground? And how long does the anvil fall? So let's draw a little picture to get a gauge of this, okay? So we have our gateway arch here in St. Louis, Missouri. And we have a little Bugs Bunny. I'm gonna just draw up top here. Little Bugs Bunny, give him some bunny ears, has an anvil, okay? He has this anvil, and he's dropping it from the top. And he is dropping it a distance of 192 meters from the ground, okay? He is 192 meters above the ground. 192 meters. And he drops this anvil, and we want to know two things. The velocity of this anvil just before it hits the ground, and how long the anvil falls, okay? So let's start with part A. Let's begin with part A first. What is the velocity of the anvil just before it hits the ground? Well, before we do that, we're gonna have to organize our information. And we already drew a picture, so our next step is to just draw a table of our givens and unknowns, right? So let's make our 4 lines, 1, 2, 3, 4, and we'll fill in our 5 variables. And I'm gonna make one little change here. And you can make this change or you can decide not to, it really doesn't matter. And that little change, if you notice, is that instead of delta x, I put delta y. Why did I do that? Well, I just want to remind myself that I am working in the vertical axis. I'm working with up and down motion. So instead of change in x or change in horizontal position, I'm going to say I have a change in y or a change in vertical position. Delta y is the same thing as delta x. It's a displacement. It's just a notation of vertical versus horizontal, okay? And I think it's helpful because when we get to projectile motion, we'll be working with horizontal and vertical motion at the same time. So it's going to be important to keep the two distinct from each other. And so for today's problems, we're going to be replacing delta x with delta y, but it's kind of a cosmetic change, right? So back to the problem. We want to know, what is the velocity of the anvil just before it hits the ground? Okay, well, the velocity of the anvil just before it hits the ground, that sounds like the final velocity to me, right? That's going to be our final velocity. So we're looking for our final velocity. And what information am I given? Well, 192 is a number, and it's 192 meters. So I know that's a displacement. It's giving me a displacement here, right? And that displacement, we need to decide whether it's going to be positive or negative. And that all depends on whether we want to decide if up is our positive direction or down is our positive direction. So for a lot of free fall problems, what I like to do is I like to make down the positive direction, okay? We are going to choose a direction to be positive, up or down, and it does not matter which one we choose to be positive. We just have to stick with it, and the math will work out. So we will get the same answer whether we choose positive or negative, whether we choose up as positive or up as negative. I'm going to say that down is positive, okay? I'm going to say that down is my positive direction, and thus up is my negative direction. So any vectors that point downwards are going to be positive vectors, and any vectors that point upwards are going to be negative vectors, okay? And so our displacement, ask yourself, is this a displacement upwards or downwards? Take a pause, think about it. All right, well, this is going to be a displacement downwards because our final position is down on the ground and our initial position was up at the top of the arch. So our anvil traveled. It traveled from the top of the arch down to the bottom. So that is a downward displacement. And so, is this going to be a positive or a negative displacement? That's right, it's going to be a positive displacement because we decided down is positive and our displacement is down. So our displacement is 192 meters, and that's going to be positive, okay? All right, what else are we given? Well, that's the only number we're outright given, but there's got to be more information here, right? We need at least 3 pieces of information here if this is going to be even a problem that we can solve. So what else do we know? Well, what has this whole section been about? Free fall, right? So what's the acceleration of my object? The acceleration of my anvil is going to be 9.8 meters per second squared downwards, right? AKA positive 9.8 meters per second. The reason it's positive is because I labeled down as positive. If I decided up was positive and down was negative, then both my displacement and my acceleration would have to be negative, right? Okay. And finally, we need one more piece of information. And it's actually going to be in a keyword. Do you see what keyword it's going to be in? Pause for a second, see if you can figure it out. And if you said that the keyword here is drops, you would be correct. So Bugs Bunny drops an anvil, and this is an important point in freefall. If we drop an object, okay, we are releasing it from rest. When we drop an object, it is not moving, and then we let go of it, and it starts to accelerate because of gravity. We didn't throw the object downwards, we just let go, okay? It wasn't moving, we were holding it in place, and then we just let go. And that's what it means to drop something. So, if at first it was at a state of rest, then what do we know? That's right, we know our initial velocity is 0, okay? Because it said drops, we know that our initial velocity is 0. So it looks like we have enough information. Let's go ahead and set up our problem. We just need to choose the correct kinematic equation. And hopefully you have your kinematic equations pulled up. But we're going to be choosing the kinematic equation that doesn't involve time, right? So we want one involving these 4 variables. And so that equation is going to be the fourth kinematic equation, which is v final squared is equal to v initial squared plus 2a delta x, or in this case, delta y, okay? All right, so let's go ahead and plug in our numbers. V final just remains v final because that is what we're solving for. V initial velocity is just 0 squared plus 2 times our acceleration, which is 9.8, times our displacement, which is 192, and thus we get, and if we want to simplify this a little bit, we get that v final squared is equal to 0 squared, aka 0 plus 2 times 9.8 times 192. So if I punch that into my calculator, 92, I'm going to get an answer of 3,763.2. And if I simplify a little bit more, then I know that v final squared is equal to 3,700-ish, okay? And so if I want to solve for v final, because I'm not done yet, right? If I want to solve for v final, I just take the square root of both sides. And, once I take the square root of 3,763, I get my final answer of 61.3 meters per second. But hold on, I just took a square root, didn't I? So really this should be a plus minus, okay? And in fact, I'm gonna have to choose plus or minus for my answer. How do I choose plus or minus for my answer? How do I know whether it's positive or negative? Well, you're just gonna have to do a bit of critical thinking here. Which direction do we think this anvil is falling? Up or down? Which direction is the velocity in? Down, right? Yeah, of course, it is traveling in the downward direction, or else it wouldn't be falling. So, guess what? We are gonna say that our velocity is 61.3 meters per second downward, all right? Remember, positive and negative just tells us our direction. So we could say positive 61.3 to say it's downward, or we could just say 61.3 downward. And those would both be specific enough, okay? And that is the end of our problem. Boom, that's it. 61.3 meters per second downward. Final answer. So let's do one more. And I'm going to have you guys do this one a bit more on your own, and then we'll see how we do, okay? All right, so for this problem, a rocket is launched straight into the air at 100 meters per second. How long does it take to reach the top of its trajectory? Okay, so if this rocket is launched in free fall, assume this rocket is in free fall, right? It's going to be accelerating downwards this whole time. So it's going to start at a velocity of 100 meters per second. And it's going to slow down until it eventually hits the top of its trajectory and falls back down. And so your job is to decide, how long does it take this rocket to reach the top of its trajectory before it starts falling back down to Earth? Okay. Go ahead and take a minute, pause the video, try and solve this problem on your own. All right. All right, if you're not having any luck solving the problem on your own, I'll give you a couple hints. And if you did do it on your own, congratulations. Just tag along for the ride now, all right? So here is a hint, okay? This rocket starts at a speed of 100 meters per second, okay? Then we are asked, how long does it take to reach the top of its trajectory? Well, we actually know something about the rocket at the top of its trajectory. We actually know the speed of the rocket at the top of its trajectory. See if you can figure out what the speed is of the rocket at the top of its trajectory. All right, well, let's go ahead and take a look. So we already kind of have our picture here. I'm going to organize our information in a little chart, like we always do, because it's a great idea and it'll give us more success with problems if we do it. So let's just run down the line, all right? A rocket is launched straight into the air at 100 meters per second. So our initial velocity, our launch velocity, is 100 meters per second, okay? And let's go ahead and say, for the sake of just doing things a little differently, let's say that up is positive, all right? It's okay if you said down was positive again, but I'm gonna say up is positive this time. So my initial velocity is gonna be a positive 100 meters per second, all right? How long does it take to reach the top of its trajectory? Well, that means we're looking for time, right? It's asking us how long is it gonna take? So how much time will pass? And we said that we can assume the rocket is in free fall, so we know our acceleration is 9.8 meters per second squared downwards. So I'm gonna give myself a negative 9.8 here. Negative because downward is negative in this problem. And so my velocity, my final velocity, I said I knew what it was at the top of my trajectory. The answer is that the final velocity at the top of the trajectory is going to be 0. Does that make sense to you? If it doesn't, think about it this way, right? Let's say I have this empty Gatorade bottle, right? And I toss it in the air. So I toss it at some speed, okay? Toss it at some speed. And as it accelerates due to gravity downward, it's going to get slower and slower and slower and slower and slower until it stops. And then it's going to fall back down, okay? So my velocity while I was accelerating is constantly changing, okay? It's constantly trending down. So at first my velocity is high upward, then it's less high, then less high, then less high, until it's going really slowly, and then it starts falling downward. So now my velocity has gone from positive to negative, all right? If we graph our velocity over time here, if we graph our velocity over time, we're gonna see that we're going to go from positive to negative. And this point at which we cross from positive to negative, that's the top of our trajectory. So the final velocity at the top of the trajectory is 0. It almost freezes in space for a moment, right? For an instant, this bottle stops moving as you toss it upward, right? So we know our final velocity at the top of the trajectory here is 0. So I'm going to go ahead and move my little rocket ship up here. I'm going to say that The final velocity here is 0 before it starts falling back to Earth. All right, our initial velocity is 100. So with that in mind, it looks like we have enough information to solve our problem, right? Let's go ahead and do that. So we know we're going to be using an equation that doesn't involve delta y, or displacement. So we're going to be using our, which kinematic equation? That's right, we're going to be using our second kinematic equation. V final is equal to V initial plus acceleration times time. All right, this is my favorite one, and probably your favorite one because it's the easiest to use, right? And so if I go ahead and plug in my numbers, I know that final velocity is 0, initial velocity is 100, acceleration is negative 9.8, and I just have t, and I'm solving for t. So the first step here, add 9.8 times t to both sides, and I get 9.8t is equal to 100. Okay, is equal to 100. And so if I want to solve for t, then all I have to do is divide 100 by 9.8, and I get a final answer of 10.2 seconds. And that is the end of the problem. Okay. Oh, wow. You know what? I just realized we didn't even do part B for this problem. How long does the anvil fall? But really, it's not much of a challenge, is it? Right? Now that we know V final, we actually could use multiple equations to solve. Right? We could use multiple equations to solve for time now that we know the other 4 variables. So I'll leave that up to you guys on your own. Go ahead and try it as a practice problem maybe. But it's basically, algebraically, you could do it the same as this, right? You could plug in your final velocity, which is 61.3. You could plug in your initial velocity, you could plug in your acceleration, and you would be able to solve for time, right? So that's the end of that problem, and that is the end of today's video. Hope you have a wonderful rest of the day, and I'll see you in the next one. Take care.